All right, college algebra. We're going to look at a general grouping of parent functions that you should be able to commit to memory. The first function would be y is equal to x. We transform that many different ways. You're familiar with that one. We're going to skip the next one. We're going to go to absolute value functions. Absolute value function y is equal to the absolute value of x. You can see that it sits above the x-axis the entire time because absolute value makes it positive. We're not going to worry about the greatest integer function. It doesn't really come up that often. I guess for this one, just put y equals mx plus b, just helping you understand the difference between these two. You may change the slope or the y-intercept. The power functions. Y is equal to x squared. Maybe you wonder why it has the shape it does. Well, first, just think when you square something, it makes it positive. So therefore, as you can see, it sits above the x-axis the entire time. Whereas if you consider y is equal to x cubed, if you cube positives, they become positive. But if you cube a negative, it becomes negative. And so therefore, cubics have both positive and negative outputs. Y is equal to x to the fourth doesn't really change shape that much. It looks very similar to y equals x squared. It just happens to flatten out a little bit more at the bottom. The higher degree you get, the more it flattens out at the bottom. And then y equals x to the fifth, it's going to look much more like the cubic one. It will just flatten out a little bit more at that spot. In fact, it's a great opportunity to investigate with your calculator. One thing that, if you want to grow as a mathematician, one thing that's important to develop is curiosity. And I think that, just having that curiosity of what happens if we change this is such a great way to understand mathematics better. But as you look at, say, x squared, I'll graph x squared. And then I'm going to graph x to the fourth. And then I'm going to graph x to the 20th. I'm going to graph x to the 100th. And I'm going to change my window a little bit because I don't need to view all these x values. But we'll look at the graph first. You can see what's happening here. The graphs kind of muddle all around themselves. It's tough to tell the difference between the two. So if we do change our window to an x minimum of -2 and an x max of +2, that will definitely make our graph look a little bit more interesting. So there's your x squared. There's my x to the fourth. There's my x to the 20th. And then my x to the 100th. You can tell how it flattens out even more. If we take this graph and we even go just one step further, we change our window so our y minimum max is at -2 and +2. We're going to get even a better view. So there's x squared. X to the fourth, you can see how it flattens out more. Then x to the 20th flattens out even more. And then x to the 100th, it almost looks like just a perfect U shape. So that's what happens when you increase that exponent. And if you think about why that happens, if you were to consider these values, obviously, if you have 0, if you take y is equal to, let's say, x to the 100th, okay? 0 to the 100th is 0. But let's get close to 1. If you take, say, 0.9 and raise it to the 100th power, because it's less than 1, 0.9 raised to the 100th power, it's going to decrease in value, and it's going to come out to be a very small value. In fact, if we try that, 0.9 raised to the 100th power, you can see that you get this e value there. That means 2.656 e to the -5th, so that's times 10 to the -5th. 1, 2, 3, 4, 5. So you actually get 0.0000265. So that means that even when you plug in 0.9, you get a value very close to 0. Whereas if you plug in 1, you get 1. Now let's just go to the other side of 1. Let's take 1.1 and raise it to the 100th power. You go just to the other side of 1, 1.1 raised to the 100th power. And you can see I all of a sudden get 13,780. And that's why this graph has the shape that it does. I'm going to take off these equals and just look at the x to the 100th. And again, that's my shape. That's why x to the 100th makes the shape that it does. And so that's one thing I encourage you to do, is to develop that curiosity about why graphs have the shape that they do, to understand it, not just memorize it as a fact, but understand it. Root functions. Y is equal to the root of x. Looks like that. You can't take the square root of a negative, so as you can see, the graph does not go over to the left. If you have y is equal to the cubed root of x, you can take the cubed root of negatives, and so you get that output. If we change it to the fourth root of x, it looks very similar to the square root, just flattens out a little bit more. And then y is equal to, whoop, I'm sorry about that. Just a little bit sharper trend, looks like the square root of x. Whereas y is equal to the fifth root of x, that, my friends, is a much sharper flattening and goes to both sides. So if we consider some other root functions, I just want you to understand what these look like. Say y is equal to, and we're going to look at cubed root of x squared, or y is equal to x to the 2/3 power. And I want you to think about what's happening. Okay, so cube root, so you might say, well, it's going to look like that. And you're partly right. So the cube root piece is going to do that. But when you square something, it makes it positive. So we'll take this part that's here, and it's going to flip it up. In fact, it looks like a bird. I like to call it the bird function. So it's just like so. If you consider y is equal to the square root of x cubed, well, that's a different scenario altogether. First of all, if you cube something, it can be positive or negative, but you can only take the square root of positives. So you can never have any negatives, and it kind of just tails off in one direction like that. So the difference between these two functions. And if you type them into your calculator, that's definitely what you get. Reciprocal functions, these are going to be heavily used. Y equals 1 over x. If you notice, there's one value you can't plug in for x. You can't plug in 0. And so there's this thing we call a vertical asymptote. The word asymptote, some people pronounce it asymptote. That's fine. Asymptote, asymptote, either way is fine. It's a Greek word. Either pronunciation is allowed. You can't get out the number 0. So y could never be 0. If you think about it, if you plug in any number for x, say 9 or 100 or 5, you can never end up getting a result of 0 for y. So therefore, there's a horizontal asymptote for 0 as well. And the graph has this kind of shape. And as you can see, y is equal to 1 over x if you were to plug in x and y values. If I plug in 1, it produces 1. But if you plug in 10, it produces a 10th. So it's the reciprocal function. It gives you the reciprocal value. Whereas if you plug in 1/100th, so a value really close to 0, you come out with 100. It flips it. So that's why you get the shape that you do. Whereas y is equal to 1 over x squared, when you square something, it makes it positive. So very similar graph, except in this situation, both graphs will be sitting above the x-axis. And there's your list of parent functions, those that you should commit to memory. This entire list you should know, okay? And I'm sure that you will. So what we want to do is we want to be able to make transformations. Suppose that we have this transformation. We'll call it a vertical shift. So we'll say that g of x is equal to f of x plus k, or g of x is equal to f of x minus k. First, identify that k sits on the outside. And because it sits on the outside, it affects it vertically. This is going to be a vertical shift. So for example, if you look at g of x is equal to x squared minus 3, the parent function is x squared. But because you have a minus 3, what's going to happen is it's going to shift it down 3 units. And so I therefore have a graph that looks like this. So graphing using transformations is a nice, quick, and easy way to operate. Now we also have other types of equations. For example, you could have g of x is equal to f of x minus h, and g of x equal to f of x plus h. And in this situation, it's a horizontal shift. And the first situation is shift to the right. And the second one is the shift to the left. For the vertical shift, the plus k is up and the minus k is down. It's important to keep that in mind because when you see the vertical piece, it says plus k, you think up. But for horizontal, it's opposite. You see this minus h, and you would think it would go to the left, but it actually goes to the right. Notice that the minus h is on the inside of the function. I know this idea of outside, inside doesn't necessarily make a lot of sense to you right now, but hopefully as we look at g of x, it will. The parent function for square root of x minus 4 looks like that. I would say that the minus 4 would be on the inside, whereas square root of x minus 4, now that is on the outside. As square root of x minus 4, the minus 4 is on the inside. It creates a horizontal shift and simply moves the function to the right 4 units. Look at the next one. The parent function is this cubic. I have 2 transformations. First of all, I have left 3, and then I have down 2. So I'm just going to take this spot right here. I'm going to move it left 3, 1, 2, 3, and down 2. And then I can draw my function over there. For the next one, I have an absolute value function, which you know to be this. The minus 4 will move it to the right 4, and then the minus 3 moves it down 3. So right 4 and down 3, there is my new function. Okay, there you have it. So vertical and horizontal shifts are usually pretty intuitive for people. But what about reflections? G of x is equal to negative f of x. Notice that the negative, again, is on the outside. This is a vertical flip. And then if we have g of x is equal to f of negative x, notice how that's on the inside. Now create a horizontal flip. Okay, so this is a little bit more involved in this scenario. But what we have going on in this situation is g of x is equal to negative root of x. G of x is equal to negative root of x. The negative is on the outside, so this is the parent function. So if we created a vertical flip, it would look like this. So the red is what it looks like. I want to be clear that if it looked like this, square root of negative x, then I'll write it in black. That way we can tell the difference between them. Then it would create a horizontal flip. And if you had both, I'll do this in green, negative root of negative x, well, that creates a vertical and a horizontal flip, both together. Now, for g of x, we have 3 minus x squared. You can see that the x is on the inside, but I want to be careful here that you should always factor it to be a positive x. So for example, I'll show you. If we were to factor the negative, we could write it as negative x minus 3. And so as you understand this graph, first of all, the parent function is a parabola, which you know. But what we're going to perform here is we're going to go right 3, and then after that, we're going to create a horizontal flip. And the flip does not always occur around the y-axis just for the parent function, but rather after you perform the horizontal flip, or after you perform the movement 3 units to the right, then go ahead and flip that function. So you can see if I move it right 3, it looks like this. And then if you flip it around that axis in which you moved it, you can see that it ends up being the same shape. So this is what that looks like, okay? Some people will treat that differently, but that's what it looks like. If you consider this function, just notice that if you did multiply this out, if you were to square the negative, it would become positive. You'd have an x minus 3 squared, and you also get that. So we'll get back to that when we get to the last one as well. Look at this guy. We have right 1. We have a vertical flip, and we have up 4. Okay, and we perform that in the order of operation which it occurs. So I'm going to move to the right 1. First of all, it's a cubic, so it looks like this. So if I move it right 1, it will look like the green. If I vertically flip it, it will look like the black. And if I move it up 4, it will look like the red. So the red should be your final result. I just drew all 4 of them so you can see how it happens for each step. Then the final one that we have, g of x is equal to negative 5 minus x. Again, I'm going to raise negative, absolute value negative, because I'm going to factor out that negative, so x minus 5. And so what you can see is we're going to go right 5, and we're going to horizontal flip about that axis of rotation, and then finally we have a vertical flip. So this is my parent function. I move it to the right 5 units, like so. Notice if I flip it around that axis of rotation, I get the same thing that I started with. And then you go ahead and flip that upside down, and you are going to get that. So I want you to turn to your worksheet. We're going to do a couple problems from there together as well. Okay, so I brought up your worksheet, and I just apologize sometimes as I've, so all the curriculum is being readjusted this year. This one is missing directions. So the direction should state to sketch the graph of the parent function and then also the new graph. So if we just go through a couple of these together, for example, the second one here, the parent function, since it's x squared, well, take that back. The parent function, since it's x squared, is a parabola. And then the plus 2 is on the inside. That's going to create a horizontal shift to the left 2 units. So that's what you should come up with. And that's all you have to do in that type of situation, okay? So a lot of these should be pretty straightforward on the front side. But there's a couple I'd like to do for you. If you flip over to the second side, let's go ahead and check out, let's see, we will do this one right here. So it's a square root function. Square root function looks like that. Because you see the plus 2 on the inside, that's going to create a movement to the left 2 units, and then the minus 3 will be down 3 units. And so that's your new function in that situation. All right. Flip over to the third one. Now we see a reciprocal function. So what I'd like to look at here, I'd like to look at a couple together. First one I'd like to look at is this one. The 2 on the top, really don't pay any attention to it. It could be a 1, it could be a 3, doesn't really matter. But what does matter is you have a negative. And the negative sits on the outside. First, let's talk about the parent function. The parent function is the reciprocal function, like such. So that's what it wants to look like. Because it's squared, they both sit above the x-axis. Now, for the movement, you can see this could be shifted to the right 3. So I move this horizontal or vertical asymptote over 3. the horizontal asymptote doesn't change at all. That's because the negative sits on the outside, it creates a vertical flip. And so this is the graph of your new function. Please just understand that in that situation, you can always graph it on your calculator to check to make sure that it's accurate, okay? I'd also like to look at this one right here. The root of 4 minus x plus 1. Because there's a way that I always like to think of these. I'll show you the way I taught you, and I'll show you the way that I actually think about it. So if you factor out that negative, it becomes a negative on the inside. Then you do x minus 4. And then you have the plus 1 on the outside. So it's going to look like this because it's a square root function, which you know. The x minus 4 is going to move it right 4 units, so we'll want to do that. The negative on the inside is going to create that horizontal flip, so it's going to come back this way. And then the plus 1 moves it up 1 unit, so it's going to look like this. So the green graph is what you actually want. Now, factoring out that negative is really important. But sometimes what I like to do is I just like to look at it and say, what would you plug into the bot or into the inside to make 0? And since you plug in 4, that means it's a horizontal shift to the right 4. I see the negative in front of the x, it's going to move it back this way. So there's a couple ways to really think about it, but the true mathematical way to view it, I suppose, is factor out the negative. If you flip it over, we'll do one more together. And what I'd like to look at here would be this one. The parent function of a 5th degree polynomial looks like such. If you would factor out the negative on the inside, it would be a y is equal to, parentheses, negative parentheses, x minus 2 raised to the 5th minus 4. So the minus 2 will move it 2 to the right. The negative will flip it so horizontally, so it will flip and look like that. And then the minus 4 will move it down 4. So the blue graph is what it ends up looking like. And again, I'd like to show you another way of thinking about that. Because here's how I think about it. What would I plug in to make 0? I'd plug in 2. So I knew it moves to the right 2. If you were to multiply this out 5 times, it would be a positive x a fifth or a negative x a fifth. It would be a negative, and so it's going to start up and finish down. And then that minus 4 will shift it down 4 units. So, you know, there's multiple ways to think about it. I might try to give you the more mathematical way of expressing it, but I've definitely had my own ways over the years as well. So, I know that it's 4 pages in length, 2 pages front and back. I do want you to know in previous years, it's been 8. So we've taken, 2 separate lessons, but we're trying to condense to some degree. And so, and a couple of these should give you a little bit of a run for your money. For example, the last problem, a lot of people find that challenging. Second to last problem, some people get stuck on that. There's problems that float around here that people do struggle with. And so don't feel bad if you need to ask questions or check the answer key, come and see me. But I have gotten rid of a lot of the more challenging ones. So hopefully you'll be good to go. 24 minutes on the dot. Have a good